Electrons. The things that flow in our cables, the things that hold atoms together, and the most complex part of said atom, but what are they exactly? Well, in this video we'll clear up everything, the energies, the orbitals, and everything about bonding. But in order to begin, we'll first have to start with... Yeah, you'll see why it's called that in a second, but first, let's start with charge. So, what is charge? Well, that's not really a question you can answer. Charge is one of these bases of our universe things, and in order to understand that, let's take a ball for example. If we let this ball go, it will fall down. That's not that surprising, but why is it falling? Well, it falling basically means that the gravity is basically, in quotes, pulling on it to move the mass down over time, but that doesn't really answer the question, or does it? This helps us to describe the movement in relation to stuff like gravity, length, mass, time, but it doesn't answer why. And that's because we can't really answer why to everything, because there are some things which just happen. They are the meaning themselves, and the only answer to why is that's just how the universe works. And this is the key to understanding what electrons are, because see, electrons are elementary particles. What does that mean? Well, let's take a look at your skin. Your skin is made out of tissue, which is made out of cells, which is made out of molecules, which are made out of atoms, which are made out of subatomic particles, which are made out of elementary particles, which are made out of nothing. That's it. That's where the chain ends. That's why they are called elementary, because there's nothing simpler. They are the pixels of our universe. They are indivisible. And that's why when it comes to electrons, you just have to accept that they don't really contain charge. They don't produce charge, they don't add charge, they are charge. And that's the first step in understanding them, just accepting the fact that you can't approach electrons as our normal physical objects like cubes and balls. No, they are elementary. So now with this extremely confusing introduction behind us, it's time to get into... So, how do these electrons interact and why are they so important? Well, imagine a magnet with two sides, the negative side and the positive side. Now imagine taking these sides and using magic, separating them in a way that they would keep their charges. Now you're left with purely negative and purely positive charge. Except positive and negative is a bit of a misnomer. In reality, a much better name would be proton charge and the opposite charge. But now, in order to actually understand how atoms work, let's take this red side and turn it into a point. And let's turn this blue side into a cloud. There. Now, because these opposite charges attract, the cloud will cloud around a point, and we have hydrogen. If we add some more electrons, like 5 more for example, then we won't really get anything. As I mentioned, electrons have charge, 2 negative charges repel each other, so 5 negative charges wouldn't even come close to our hydrogen. That's why we need to add some more positive charge to create a carbon atom, which would be positive enough to actually attract these electrons. But this time, something more interesting happens. Because, yeah, we like to think of charges as just these simple numbers. So in this case, the nucleus would have a charge of 6, an electron cloud would have a charge of -6. But in reality, there isn't really such a thing as a nucleus or an electron cloud. We just call the clump of these protons in the middle a nucleus, but it isn't quite as simple because these don't really exist as a simple point. And because of that, electron cloud wouldn't just be this perfect ball, only a much more complex shape. So just like if you have a squishy ball, if you push on the side really hard, it will bend. In the same way, our electron cloud arranges itself into this complex shape because of the charges pushing on it. But now, here's the problem. In chemistry, you really often need to know how these electrons interact together, and thus we need to know their shape. So, is there a simpler way, maybe, to describe their shape without the whole simulating quantum mechanics problem? And the answer is... yes, there is, and here's where we enter the domain of the quantum numbers, and there is 4 of them. Let's start with the first one, which is the principal quantum number. When it comes to the principal quantum number, you can think of it as the distance of the electron from the nucleus. So the higher the number, the further it is on average, and there are 2 reasons for why it's important. First of all, the further it is from the nucleus, the more energy it needs. Just like if you have a ball, you need some energy to move it further from the ground. You need some more energy to move it even further from the ground, and the same thing for our electron. Same thing. So the higher the principal number, the higher the distance and energy on average. But there is a second thing, which is just as important, and that's the fact that the further the electron is, the more freedom it has. So remember carbon and those weird hourglass shapes? Well, that's why they happen. An electron with the principal quantum number of n equal to 1 has only one possible shape, a ball. That's all it can form. But in the carbon atom we have 2 electrons with n equal to 1 and 4 electrons with n equal to 2, so further away. And that's why some of these can actually achieve this hourglass shape. They are further away, they have more freedom. And that's where we get to the second quantum number, the azimuthal quantum number, or L. For n equal to 2, we have L0 or L1. For n equal to 3, we have L equal to 0 or L equal to 1 or L equal to 2. And that's because, as I mentioned, electrons with more distance and more energy have more freedom to choose different shapes. The number L tells us the shape of the electron cloud, but if you want to be technical, then it's not really shape of the electron cloud, only the shape of its probability. And since its probability is governed by something called the psi function, this is actually a pretty surprisingly mathematically accurate of an analogy. So just as a quick recap, first we have the number n, which tells us the distance from the nucleus. The higher the n, the further away it is, but you need more energy to reach the further distances. That's why electrons first occupy the closer distances. Then the further away it is, the more freedom it has to achieve different shapes. Shapes which are governed by the L number. That's why the higher the n number, the more possible L numbers. Now next we have ML, which is a bit confusing, but you can basically think of it as a direction? Kind of. Basically we can take our hourglass shapes and each of them has their own ML value, which represents a different direction, but for more complex shapes, it's more like a mathematical idea of direction rather than the simple three-dimensional direction. I mean, that's why I'm animating this, because, well, this is something that's easier to show than actually explain. Increasing the n number, increasing the size and waviness. Increasing the L number, changing the complexity and shape. Increasing the ML number, changing the orientation. Great! Now we can finally get to... Everything you've learned so far would be only useful for quantum mechanics, trivia, and getting an intuition behind different descriptions of electron configuration. But in this chapter, we'll go over the molecular orbital theory, which I absolutely adore, and that's because it's simple, it's intuitive, and it explains everything about every kind of bonding. No, that damn asterisk again. So for bonding, we'd like to simplify everything a fair bit, because whilst right now you do know the physical kind of meaning behind these numbers, we still need to get over how to use these numbers. So let's start with shells. Here we have different shells, each one with a different principal quantum number. So first principal quantum number, second, third, so on. Then we can divide them into subshells, like this. These subshells are divided by the azimuthal quantum number, so they represent the change in this shape. Now this is especially cool because we can move it like this, and the height of these boxes isn't random. The higher you go like this, the higher the electron energy. So an electron right here has lower energy than electron right here. Now the last thing we can do is we can divide these subshells even further into orbitals. And for all of these orbitals we can only have a maximum of 2 electrons with different spins. Got it? The higher the electron, more energy, they start filling it from the bottom up, and each square basically represents one of these directions. Here you can see what the previous orbitals truly were like. Anyhow, in order to understand bonding, we'll first have to get through a phase. The phase. So what is phase? Well, you have to understand that in quantum mechanics almost everything behaves kind of like a wave. What do I mean by that? Well, that's kind of difficult to answer and kind of difficult to describe too. But basically, here's the idea. If we have 2 electrons with opposite phase, and if we bring them together, they will repel each other. if they have the same phase, they will attract. Now this may seem a bit weird because we're used to the idea that opposite charges attract, and that's true. Opposite charges do attract, but phase isn't charge. And that's precisely why I said earlier that negative charge is a misnomer, because in reality it should be called opposite charge. But with phase it's different. With phase it's actually negative. In order to understand why, let's imagine two functions. A function like this and a function like this. Now we can take these functions and add them together. There, we end up with a larger bulge in the middle. That's basically what happens when we have two electrons and we bring them together. Remember what I said about functions in the previous chapter? Well, the way quantum mechanics works is that we don't actually have an idea of where the electron is. Instead, what we have is the psi function, which tells us the probability of it being in any of these spots. So right here, high probability of finding the electron. Right here, low probability of finding the electron. That's why if we have this function describing the probability of finding the electron in any given spot, and this other function describing the probability of finding the other electron in any other spot, now what we can do is we can graph the function describing this probability. So probability of both of them summed together. After we square it, I'll explain why we square it in a second. Right here, it's extremely probable to find this electron. Right here, a bit less, and right here, practically no chance of finding it. Now we can see why if we bring two electrons together, they can merge their clouds. Now let's introduce phase. What phase would basically mean is us having the same function, but in the negative. You can see that for a single electron it changes nothing. We still square it and the probability ends up being the exact same, because square removes the negative sign. But if we bring two electrons together, when they are out of phase, what we end up with instead is this. And then we square it to get the probability, and you can see that the probability changed pretty drastically. And that's what phase is. And that's why two electrons in phase attract, whilst two electrons out of phase repel. Let's go over it again, because it's a lot of maths and I really want you to understand. One electron, second electron. We add their probabilities, square them, there we go. That's the probability we end up with. But why am I telling you all of this? Well, that's because it's actually really important when talking about bonding. Let's take two hydrogens for example, and based on the information I've provided you so far, you should already know a fair bit about what their electrons should look like. First of all, if you remember, electrons first fill the space closest to the nucleus, which means its n number will be equal to 1. That's the smallest possible one, and since it's so close, there's only one possible shape, and that's the sphere. That's why this is what hydrogen would look like. Now let's introduce the second hydrogen and let's have them bond. How would this work? Well, let's introduce some notation. For each hydrogen we'll have a bar. This bar represents an orbital. In this case, n equal 1, L equals 0 orbital, which just translates to the orbital of distance 1 from the nucleus with the 0th shape. You already know the quantum numbers. Now what happens when our atoms bond? Well, these two orbitals join together and create two new orbitals, one with higher energy and the other one with lower. The lower energy orbital would basically mean both electrons having the same phase, so this situation. The higher energy orbital would basically mean both electrons having opposite phase, so this situation. Now I really want to pause here for a second because a lot happened and it's kind of crucial that you understand what happened. We have the first hydrogen orbital and the second hydrogen orbital. They bond together to form two new orbitals. So unbounded orbitals, bonded orbitals. When it comes to these bonded orbitals, one of them ends up with lower energy. In order to balance things out, the other one ends up with higher energy, so that the average energy remains the same. Now when it comes to these electrons together, they have two options. They can either be out of phase or in phase. That's why we have two orbitals here. But it's much easier for them to be in phase than out of phase. That's why the in phase requires less energy and the out of phase requires more. Alright, we all understand? Is it clear as mud? Close enough? Okay, I really hope so, because with this background, bonding itself is actually kind of obvious. So we have these orbitals, and originally each hydrogen had only one electron. Now, each orbital can have 2 electrons, so when they join to these new orbitals together, these 2 electrons have a choice. They can either go for the orbital that requires more energy, or the one that requires less. Guess which one they will choose? Yeah, in our universe, things really don't like having energy, and so that's why balls fall to the ground, that's why light bulbs glow, and that's why things heat up. They want to get rid of their energy, either as movement, light, or heat, so I guess movement. In the same way, our electrons want to get rid of their energy, and just go for the lower orbital, and there, we end up with hydrogen gas. Now this is really f***ing awesome, because have you ever wondered, for example, why things bond? Like, what force is actually keeping the atoms together? Well, the answer is nothing! There is no force keeping them together. That's just when they are together, they have less energy. Imagine it as a ball in the air. That's the hydrogens when they are alone. When they bond, that would be kind of like the ball falling. Now, when it falls to the ground, you can see that there isn't really a force keeping it down there. Even if we remove gravity completely, it would still stay down. So what force is keeping it down there? No force. Nothing. Nothing is keeping it on the ground. You just need energy to actually move it. That's why atoms bond. They are just more stable together than apart. See this difference in energies? That's what you need to bring these electrons up, back to their non-bonding orbitals. Isn't that cool? But there is one more thing I'd like to go over, and that's because noble gases don't like bonding. Yeah, I mean, we really often learn that noble gases aren't all that reactive and they don't really like bonding, but why is that? Well, let's go back to our hydrogen bonding example and replace them with helium. What would this situation look like now? Each helium atom has 2 electrons, so they first fill the lower bonding orbital and then there are still 2 electrons left. So the only place for them to go is the anti-bonding orbital. And yes, it is exactly what it sounds like. Remember the out-of-phase scenario? Well, you can see that this out-of-phasiness keeps the electrons apart. And that's precisely what's happening. You can think about it in 2 ways. Either the first way, so we have 2 electrons which are bonding them together, and 2 electrons which are pushing themselves apart. So basically, these pull just as hard as these push, so atoms end up with nothing between them. Or the second way, so basically here we're able to give energy away, but we need additional energy to make this happen, or to make it happen. And that's why there's no bonding. It's not giving any energy away, and thus it's not any more stable than just 2 atoms apart. Also, another thing, have you ever heard of something like sigma bonding or pi bonding? Well, there's also delta, which you might have not heard of, but why is delta a thing? Well, it's because whilst these orbitals are the s orbitals, because for Azimuthal quantum numbers, 0 means s, 1 means p, 2 means d, 3 means f, I don't know, chemists just don't like numbers. So these are our s orbitals, but when they bond, they become sigma orbitals. When we have p orbitals, when they bond, they become pi orbitals. When we have d orbitals, when they bond, they become delta. When we have f, they bond, they become phi. And what's really nice is that the higher the Azimuthal quantum number, so s to p to d to f, the lower the difference in between those energies. That's why S is the strongest bond. That's why sigma is the strongest bond, because it has a huge difference in energy. So basically you need a lot of energy to bring those electrons back up. And yeah, this is all cool in theory. I mean, in my opinion, really cool. It's my favorite bit of chemistry, but how is it actually useful? Why isn't water flammable? Let's take flammable hydrogen, mix it with oxidizing oxygen, and you get water. Why isn't it flammable? Well, in order to answer that question, we'll first have to ask the question of, why is hydrogen flammable? Well, it isn't. You see, individual atoms can't really be flammable, and properties of hydrogen depend not really on the hydrogen itself, only on its bonds. Hydrogen isn't flammable, hydrogen gas is. When we set it on fire with oxygen nearby, it explodes. But why is that? Well, let's start by introducing our players, hydrogen gas and oxygen gas. With hydrogen gas, it's simple enough. Here we have the 1s orbitals, both with only 1 electron. Now when they bond, they merge into sigma orbitals. this time with different energies, and occupy the lower energy one. We've already been over this before. For oxygen is the same situation except more complex. We have more orbitals to join and they make up some more complex bonding and anti-bonding orbitals, but in the end it just looks like this. Oh, and by the way, this is why only valence shells matter, so the outermost. It's because all of the lower shelled electrons just end up filling, you know, both bonding and anti-bonding orbitals. So in this case, for example, the 1s orbital doesn't matter. It's not contributing to the overall bond. Now that we've got those out of the way, let's take a look at water. With water, I won't go into depth too much, and that's because it's really complex. But the point is, when oxygen bonds with hydrogens, you end up with these bonding orbitals. And the key thing to notice here is that the water bond energy is lower than hydrogen and oxygen. And that's not like a fun thing to notice or like an effect of the explosion. It's the answer to all questions. You see, when you have your high energy oxygen and high energy hydrogen bonds and you switch to lower energy water, this extra energy can't just disappear. So where does it go? Well, that's the fire, emitting that energy as light and heat, the energy of these precise bonds. And this is what I'd like to focus on, because this finally answers the chain of why. Why isn't water flammable? Why is hydrogen flammable? Why is hydrogen bond responsible for flammability? Why is hydrogen bond higher in energy? Why? Nope. That's actually it. The molecular orbital theory explains it. We've already been over orbital energies, so we know why these certain orbitals have different energies, and we've been over bonding, so we know why they merge. There is no more questions. And that's the point of this video. Most people know chemistry from their schools, their high schools, and just leave it there because they end up hating it. But that's only because chemistry in schools is being taught wrong. In schools, you'll really often hear about topics like shells, sigma bonds, bonding order, oxidation state, and so on, but they are never fully explained. They always leave you wondering why does that matter, why does that happen? And that's why I wanted to make this video. Because when I said everything about bonding, this is what I meant. This is the true foundation, and with this foundation, with this better understanding, I hope that you are willing to give chemistry another try. Because now you understand everything about electrons. Except spin. Yeah, when it comes to the base quantum numbers, remember the Asimov principle, stuff like that, there's also a spin number, which I completely omitted because it's irrelevant to most of chemistry and unbelievably complex. I didn't want to muddy the waters, but don't worry. I do plan on making a sequel, and also have actually finished half of the video about electricity. That's actually why I haven't uploaded anything in a while. I have this video, which is in the works. I have this video, which, yeah, that's really cool bucket full of liquid that I'm also working on. There was this video I currently made, a video I'm making on streams, and not gonna lie, I may need some help. So if you'd like to get exclusive previews to these videos, then Patreon is there for you, where the preview to the first video I mentioned is already on there. And memes from the current project I have going on, like this one. I'm a bit, not gonna lie, I'm in a bit of a financial pinch at the moment. And also selling out. What about your streams, you ask? Well, I also stream every single day for charity. And actually, in 3 days, we'll be streaming the 500th charity checkup, because I've been streaming every single day for the past 500 days. And I would really recommend you join in. I'll also be donating $500 to charity. That's kind of one of the main reasons for why I'm in this financial pinch. And I just, I would really recommend you join in and have fun. I have a Discord server too, and I guess that'll be it. I guess that's the wrap up of this video. Hope you liked it. Well, electrons, and soon I'll hopefully make another one. If you have any more questions, feel free to ask them in the comments, and for now, that'll be it. Thank you everyone so much for watching, and have a great day. Bye.